Hi guys, welcome back to Nitronics. It is the end of 2023, and to wrap out the year, I wanted to show you how I test/validate all of the electronics projects that I build on my channel/blog. So today I've partnered with Digilent to take a look at some of their new test equipment things, current FPGA dev boards, but that's what I wanted to explain to you. So before we get into things, there's a few disclaimers to go over to make all the lawyers happy. Digilent is sponsoring this video. They have sent me this equipment. They're great people over there. I love working with them. I've been working with them for several years now. All opinions in this video are 100% my own and do not reflect the opinions/thoughts of any company that I am currently or have previously been associated with. With all those disclaimers out of the way, let's get into the video. So for those of you that may not be familiar, Digilent has a line of USB oscilloscopes for their test equipment lineup. This includes the Analog Discovery 2, the AD2, the Analog Discovery 3, the ADP 5250, and then that little brother, the ADP 3450. This year, they released an embedded Linux image specifically for the Eclipse Z7, one of their tried and true FPGA development boards, that contained a Waveforms application that couples with the Waveforms application that runs on a host PC to act as an interface to all of their USB oscilloscopes. I've been experimenting with how does the Eclipse Z7 with Waveforms stack up to their other lineup of USB oscilloscopes. And there's a big key way that it does that I am personally a very big fan of. So I actually started my career as a test equipment engineer, where I got very familiar with the professional industry standards of test equipment that you use. The full-blown oscilloscopes, power supplies, waveform generators, everything that you're gonna use on a professional bench that are all the tens of thousands of dollars. And one of the power supplies that I became a very, very big fan of was the Keysight N6700 series. And the reason that I really liked that power supply was it had a modular feature. It had 4 slots in it. So with those 4 modular power supplies, I could swap out different modules depending on my application, whether or not I needed a 30-volt supply, a 10-volt supply, so on and so forth. That was very handy. And that's where I feel like the Eclipse Z7 and having waveforms available on it is a really great comparison for that on the lower end hobbyist level, or even just a basic bench setup. Because the Eclipse Z7 has Digilent's Zmod connector for that. The connectors for Digilent's Zmods are a syzygy compliant interface. Syzygy, which I think is the right way to pronounce that acronym, it's SYZYGY. It's a high-speed I/O interface that was created by Opal Kelly back in, I think, about 2017. It was intended to be somewhat of a middle road between the super high ping count high-speed I/O standard of FMC that a lot of FPGA development cards use, and then the lower end general I/O PMOD that Digilent introduced several years ago. And being that middle of the road allows you to have a smaller footprint, still have high speed, but not just be the giant, I'll put it on the screen, an FMC takes up a lot of real estate. It's kind of the best of both worlds there. These Zmod carrier boards come in a few different flavors at the moment, or a few different types. You have the analog to digital conversion based side for the oscilloscope aspect slash functionality, and then you have the digital to analog side or flavor of the Zmods, which are for the analog waveform generation or AWG functionality. So I have one of each on my Eclipse Z7 here. And the other thing I think is worth noting is when I made the comparison to the Keysight N6700 power supply, that being kind of the big fancy Cadillac of it all, The base of that start, I think last time I looked, was about $10,000, and then each module is somewhere around $2K, give or take. As of the time of filming right now, you can buy the Eclipse Z7 bundled with 2 Zmods, depending on how you want to mix and match these guys, for just under $650 at the moment, so quite a bit more affordable on this side. I also have one of the other flavors of the ADC Zmods. This is what's called the Scope Zmod. So it comes in a couple different variants, actually 3 specific variants. The main differences being is that the ADC chip on it comes at different sampling rates, so you can have all the way up to 125 megasamples per second, and then the low end is 40 megasamples per second. And then obviously the price will be respective of that, with the higher sample rates being a little bit higher on the price end. The other flavor of the ADC based Zmod is the Digitizer Zmod. It's up there in the 125 megasample per second sampling rate. So even though it's the same sample rate as the high-end Scope Zmod, it's been tailored with its circuitry, with DC coupling and other things like that, to be geared more towards RF measurements, which I'm going to show you some of what I've been using it for over my past projects for the year. Let's get into how I set this up, because the really cool thing is I've been using this as a bare board over the past several years, ever since I've had it. And with the introduction of waveforms for the Eclipse Z7, I noticed that there's this handy little enclosure that is available for the Eclipse Z7. So I thought I would take the time to assemble my Eclipse into its little enclosure to then start demonstrating its capabilities with all of my projects that I've been working on over the past year. So let's get into that. First things first, to the enclosure install. We need to remove the 2 metal standoffs from this side, because I noticed they're actually further out than the ones on the side with the Zmods, and that doesn't fit in our nice little aluminum track here. Righty-tighty, lefty-loosey. Helps to not tighten it when you want to loosen it. We've got our little power plates with our power switch and CPU fan. So with our power switch, to push it through, there we go. Leave that in the off position for now. And then we've got 2 screws, or 3 screws to hold the CPU fan. Oh, it looks like there are these little long guys, and there are only 2. So we'll have the wires facing down on the inside here. Okay, so after a bit of torque, I got my fan screws in. Didn't think you guys needed to watch me struggle through that. We're going to put this little green plate on, and then we can take our little enclosure, and we need to, so this plate goes on the side with the LEDs, the Ethernet port, and all of that. So we're gonna slide this in the 3rd rail here. Slide that back out a little bit, because we need to connect our on-off switch, which is, there's a couple little jumpers here right next to the power switch that matches the 2 pins here. Okay, so it looks like the red side is closest to the power switch and black is closest to the edge of the board. And then we need to plug in our fan here. So there's a CPU fan on top of the Zinc 7000 chip that is the core of the Eclipse Z7. And there's an extra white header over here that is for the CPU fan that's going to pull in air into the enclosure. Thankfully keyed, so I can only plug it in the right way. We'll slide that back. We've got our 4 little screws that are going to hold everything in the front here. Okay, so got all that screwed down, and looking pretty nice so far. We'll get that all lined up there so we can still get our SD card in and out. And now we need to put on the rear plate. So for the rear plate, we need to take the nuts off of each of the SMA connectors because they're going to go on the outside of the plate. That's part of what's going to hold it in place. There's nothing more awkward than waiting for someone to unscrew the nut off of an SMA connector, I've learned over the years. This is riveting content, I know. I'm sure you're all on the edge of your seat. Can you tell I'm fun at parties? I'm just gonna keep going with these awkward one-liners. Now that I got all the nuts off of the SMA connector, we can go ahead and put the other panel on here. Put the green side on. Get the 4 screws in the face panel and we will be ready to rock. That is our enclosure all ready to go, which I have to say, it's pretty exciting. I'm a sucker for a cool case on anything. While I was assembling this, it did dawn on me. I wasn't sure if I completed my thought earlier in the comparison with the Keysight N6700 power supplies, so the same way I could swap out the modules in the N6700 power supply, that's what we can do with the Zmods on the Eclipse Z7 to swap out different Zmod, whether I need 2 scope Zmods to have 4 total channels of oscilloscope, or I can have 1 scope, 1 AWG, or swapping out the different types of scope modules depending on the sample rate that I need, or upgrading to the digitizer ADC that we need. So before I put this in here, I installed the AWG Zmod on the channel B, and then I have the digitizer Zmod on channel A. The Zmod digitizer tends to be what I've been using for most of my projects so far. Since it has a higher sample rate, it kind of covers everything that I've been working on, including more of the SDR RF applications, which is especially important with that extra circuitry with the DC coupling to get better fidelity signal on the RF spectrum in the spectrum analyzer. The only downfall of my digitizer, or well, not downfall, well, the only feature that would have me switch back over to my scope Zmod that has the same sampling rate is the fact that the maximum voltage input of the digitizer Zmod is plus or minus 1 volt, whereas the scope Zmod with the equivalent ADC sample rate of 125 megasamples per second has a high and low gain setting, meaning that the input voltages can be plus or minus 1 volt max on the low gain setting or plus or minus 25 volts on the high gain setting. Just wanted to make sure I rounded out that thought earlier because I'm realizing I've gotten scatterbrained. But anyway, let's see this guy in action. Okay, so I've got everything hooked up here. I've got the power hooked up, and then because I'm using Waveforms, the USB connection to my host PC, instead of being on the JTAG UART of the Eclipse Z7, is actually going to go to the OTG USB port. Got, of course, my SD card here installed with the Waveforms Petalinux image. On we go. Got everything installed and powered up. I do have Waveforms running on my host computer. As far as the installation of Waveforms on a host device, how to install Waveforms on an SD card for the Eclipse, that's all documented both on Digilent's website and my blog on Hackster. You can find all of that. Another bonus thing is the Linux image for the SD card that goes in the Eclipse. It's already preloaded in an installation directory of Waveforms, so once you install Waveforms on your host computer, you can dig through that directory and find the image to put on the SD card, so there's no extra, you don't have to install Vivado or Petalinux and to build the image from scratch, which I think is really great, so you can just get going with it right away. So the next thing I wanted to kind of take a look at was the different type of connectors and probes that I use to actually connect to my circuits. The first option we have that Digilent sells on their website are these awesome little SMA to alligator clip connectors. I have 4 of these since I can have up to 4 SMA at a time. I've mostly used these, but I also found some SMA to BNC adapters on Amazon. You can get a fairly cheap set, which is perfect for benchtop stuff. Obviously more crazy, higher level RF stuff is not gonna do great in these because these are just, like I said, cheapies and BNC. That means I can then use my regular BNC scope probes that I would use with any other regular oscilloscope or any, like my ADP 3450. So I can install, and now it works with the SMA ports of my Eclipse board. So I've picked a few projects over the past couple years to highlight how I've been using the USB oscilloscope within the Eclipse board. The first of which is my awesome little Hemholtz coil snow globe that I built. It looked really cool. Once I got it working, the electromagnetic field that it emitted wasn't quite as strong as I thought it was going to be, or what I calculated. So the first thing I wanted to do was make sure that it was drawing the right amount of voltage and current that I had calculated. That's kind of the first place you typically start. If something's not working the way you think it should be, I like to start with the input power supply. Is it drawing what I expect? So with the voltage setup, that's pretty easy. I just have my 2 inputs and I clip my plus or minus and connect to my Eclipse Z7. Very straightforward, power it up. This guy I had running at 3.7 volts off of a little lithium ion battery, and I had created my little constant current driver circuit to supply it with a constant 20 milliamps because with the gauge of wire that I used for the coils, the maximum current that the wire could carry was 22 milliamps, so I spec'd it to drive a constant 20. And the voltage measurement looked fine. It looked great. I saw the power up waveform, the power down waveform, all within the Waveforms application on my host PC, which I have that all detailed with screenshots in one of my Hackster posts linked below. The next step after that is making sure that it was actually drawing the constant 22 milliamps I was expecting it to. This gets a little bit tough because with any oscilloscope you can only measure voltage because you're measuring a potential between 2 points. To measure current, however, you have to measure the current flowing through a given device. So to measure current with an oscilloscope, you have to insert a device into the circuit to measure that current, to let it flow through. So that's referred to as a current viewing resistor or a shunt resistor. And you typically spec it out to where it's going to be small enough, low enough value that it's not going to impact the behavior of the rest of the circuit, but also not 0 ohms because then you'd be shorting out the measurement of the probe at the scope. I added a small little 10 ohm resistor here to the input of my coils and then powered it with my benchtop supply. And you're probably wondering, well, your benchtop supply shows the current, so why measure it again with the scope? The caveat to that is when you're seeing the current from a power supply that is only a 2 signal power supply, you're measuring the current at the probes of the power supply. And given the extra impedance of going through a cable such as this, you're not reading the exact current that is at your device under test. The typical resolution for this in a more professional setting is a 4-wire measurement setup where you have an extra set of cables coming out to the actual device under test. However, on my smaller bench setup, I am using the Eclipse board to measure my current viewing resistor here to get an actual measurement of the current, and then I configured waveforms. I added an extra custom measurement, told it the value of my CVR so I could actually see the power up and power down current waveform and verify that yes indeed, my coils were drawing the 20 milliamps I expected, which ended up having a big impact on my final measurements, because when I first looked at what the power supply was showing, it was showing that my coils were only drawing about 17 to 18 milliamps, whereas when I actually properly measured it with a CVR at the input of the coils, it was my expected 20 milliamps. That brought me back from thinking, okay, maybe there's something wrong with my current driver circuit, to the output magnetic field that I calculated just wasn't as strong as I thought. Because the relative measure of Gauss coming out of my coils, that's a little bit tough to figure out what I want to impact the Fahrenheit shavings that were in the snow globe. That was project number 1. So the second project I picked out to highlight this year that I used my USB scope for was a little bit more of an experiment / exercise in analog electronics again. If you've been following the channel for any amount of time, you know that I'm mostly a digital domain type person in FPGA design. And I do a lot of DSP type tutorials with fur filters and other types of digital filtering. So I kind of wanted to take a step back and look at the frequency response of some OG Circuits 101 RC filters. So I created a low pass, high pass, and band pass filter with my breadboard right here. And then using the network analyzer function in Waveforms, I attached a channel of the scope on the input, the output, and then also had one of the channels of the AWG creating the waveform that goes into the circuit, so that I could measure what the frequency response of each filter looked like across a sweeping range. So that was very handy. That's also a common test that you run on quite a few circuits, is you want to know what your frequency response is going to look like. So I thought that was a great exercise of, I was able to calculate these, I knew what it should look like. Also just kind of curious of what the tolerance of my little breadboard parts are, as they've been sitting in my bins for quite a while, because I did come across a few of my electrolytic caps that were definitely not good anymore. And I immediately saw that on the network analyzer. Again, I'll have that whole project tutorial with the details linked below with all of those screenshots. Let's take a look at my final series of projects for 2023. The third project I wanted to highlight that I've been working on this year, that I've been using my Eclipse Z7 with Waveforms to validate, is this cool little direct digital synthesis module that I found. My Amazon weirdly knows me too well again. It suggested this little $20 board that's based on the AD9850, which is a direct digital synthesizer that based upon what control word you send it on the digital interface, it outputs the respective sinusoid at that particular frequency and phase. So I think this is the project where I feel like this really shined here, my Eclipse with Waveforms, because I implemented several elements of the test equipment within Waveforms for that. And I'm gonna hook all this up here. The first of which being the logic analyzer side. So the two PMODs that are below the SMA ports on this side of the Eclipse board, that's where you can input digital I/O to link back to the logic analyzer within Waveforms, where you have interface protocols you can test against. You can just add plain digital I/O, that type of thing. The reason I needed to do that was because the serial interface to the AD9850, while it was very close to a SPI interface, there was a little bit of difference in their frequency update signal, which behaved similarly to a chip select signal in SPI, but a little bit different. So I ended up just bit banging the interface from a Python script on a little Raspberry Pi 0W, and then driving my actual AD9850 DDS synthesizer chip. So I was able to take all of the pins here, put it back into the logic analyzer, and as I was modifying my bit banging script to manually create that digital interface, I could see what my code was actually creating in waveforms, and I was able to prove that in. I did find some weird kind of pitfalls that route. Going back and reading the datasheet on the 9850, I found I need to always pulse the reset button in between frequency words. I needed 18 clock cycles with no data to give the 809850 settling time. All of these things that I was able to validate with the logic analyzer and waveforms, and then also at the same time have the two analog outputs from the board connected back to the SMA to my digitizer, so I could see exactly when I sent a certain control word, I could validate immediately that I was getting that particular frequency and phase of sine output. So that was a big thing, having that combo of logic analyzer and oscilloscope and and spectrum analyzer all in the same thing. Very, very much appreciated. And another thing worth noting is the AD9850 on this particular board had a range from 0 megahertz to 40 megahertz, which is where I ended up using the digitizer for. So if you're not familiar with test equipment, if you have a scope, whatever your max sampling rate, you cut that in half, and that is the maximum frequency target signal you can measure. That goes back to Nyquist's theorem that your sampling frequency has to be at least twice of the measurement target to make sure that you can actually view it appropriately. So with 125 megasamples per second, that means the maximum frequency you can measure with the digitizer Zmod is about 62 megahertz. So I felt like that was perfect for measuring my 0 to 40 megahertz output, because I kind of wanted to see what I could do with the AD9850 board, whether I use it as a local oscillator reference, a clock reference. I did end up creating a cool little baseband 2 FSK modulator with it, which is where the digitizer came back in, validating that I could actually see my message, my ones and zeros bits in my message translated into the appropriate transitions of frequency 1, frequency 2 coming out of the AD9850. I figured I would hook this project up and let you see it in action, since it utilizes the most on my Eclipse board. So let's get into that. So like I mentioned earlier, I use the logic analyzer function in waveforms to measure the serial input interface of the AD9850. So I mapped out the PMOD ports as far as what's the power, what's the ground, and what's all the digital I/O in my project write-up, which of course is linked below. So, got power on the outside. This is my ground. And then my 4 signals for the digital interface. And then the AD9850 actually has 2 sine wave outputs, so I connected those 2 outputs to channels 1 and 2 of the digitizer Zmod. I chose the breadboard setup because this little PCB module actually came with pre-soldered headers, so this was the easiest route to get up and running. There we have my test setup. I've done quite a bit with measuring the AD9850. The first thing I did was, after I had the interface working and I validated that I was getting the correct frequency and phase of sine wave output, the next thing I did was some basic RF test measurements that I kind of do to any SDR or RF type device. The first of which was I switched over to the spectrum analyzer function in waveforms, and I validated the transmit center frequency offset, which is where say you tell the device to output 10 megahertz, you then measure the output, and whatever point on the frequency spectrum has the most power output, that's the frequency value you measure as the actual output, and then measure how many hertz off that is. The other common or most basic starting point of RF test measurement that goes hand in hand with that is transmit output power. So, and that kind of goes hand in hand with it because, like I mentioned, you pick the point on the frequency spectrum that has the highest output power, and that's what you consider the actual transmit output frequency. So you kind of get both measurements at the same time. So I was able to validate that across the frequency range from 0 to 40 megahertz. On the AD9850, I actually only went down to about 10 megahertz because I didn't really plan to use much more below that for any of like my baseband processing. The second thing I did in the spectrum analyzer function on Waveforms was measure all of the spurious outputs. Spurious outputs, or spurs, are a side effect of the quantization process of any sort of analog to digital or digital to analog chip, just because there's a finite number of bits that you can use to resemble an analog signal. So when you're creating that analog output with a certain number of digital bits, there is some level of spurs that end up because you're not perfectly creating that analog output signal, if that makes sense. I have a more detailed explanation in the project links below. That's another good test I like to run on any sort of ADC chip, especially one being used as a direct digital synthesis type chip. The other thing I was kind of concerned about is when I bought this little $20 DDS board off Amazon, it showed up in regular styrofoam in a normal plastic baggie, like a food baggie. So zero ESD safety there. So I'm honestly kind of surprised it performed at all. And then, like I mentioned, the final test I went through is I made a little 2FSK baseband modulator with this guy. So let's take a look and see what we have on Waveforms. Okay, so now that I've got my little DDS target circuit all set up and ready to measure, I've come back to Waveforms here on my computer. One of the other things I like about Waveforms is you can save workspaces, so whatever tabs you open for each test equipment functionality, you can save that whole configuration, so it'll just reopen, which, considering in my former life I made a living on creating automated test equipment software, I love this part. This does a lot of the grunt work for me. So you can see I've got my logic analyzer. Oh, it even saved my last measurement here, looking at the so you can see I had both the I added each discrete I/O as a digital I/O signal here in the logic analyzer, and then just to see how closely it did behave to SPI, I added an SPI interface and mapped it to the respective digital I/O pins. So that's another cool feature in Waveforms, is you can add the same digital I/O either just as a plain digital signal to monitor, or you can add it in some sort of protocol format and then trigger off of that particular protocol format, whether it's you want to trigger it off the transfer starting, the transfer ending, some particular signal within the transfer, like say if you want to see the data line in an SPI interface go to a certain value, you can set the trigger to that specific value. So that's what I have here. You can see I was sending a little 1 megahertz control word and the various elements of actually clocking that control word out to the AD9850 from my Raspberry Pi. And then of course I've got my scope open here to see the analog output from the AD9850 in the time domain, and a spectrum analyzer function open here so I could actually see what that looked like, that same analog output signal in the frequency domain. So you can see it saved my last capture here. Looked like I had it at a center of 10 megahertz. So you can kind of see what I was talking about. I've got the main fundamental frequency, And then all these little guys above the noise floor are those spurs that I was talking about that you get from any sort of ADC or DDS type chip, direct digital synthesis chip. I'm connected to my little Raspberry Pi Zero over SSH, so let me set all these triggers and capture some data here. So I have my DDS compiler outputting a 10 megahertz signal. Like I mentioned, I've got it running here on the spectrum analyzer. One thing I do want to point out is that of the different functionalities within Waveforms, so like the oscilloscope versus the spectrum analyzer, all of that, if two of the same functionalities use the same Zmod, so both the spectrum analyzer and the oscilloscope need the same circuitry on the digitizer Zmod, you actually cannot run them both at the same time. But I did do independent captures, so I've got it here on the spectrum analyzer that's currently running, but I had also captured it on my scope as well. However, because the logic analyzer is separate, it's using the PMOD down below, I can run this independently at the same time as either the spectrum analyzer or the oscilloscope, or if I were using the DAC at the moment, the waveform generator function. That's what I have running here. Captured my last control word, and that's it. That's the Eclipse Z7 running waveforms in action. So thanks for watching along if you made it this far in the video. Like I mentioned before, all of the corresponding write-ups for each of the projects I mentioned, all of the how-tos, how to recreate everything, is all going to be linked in the description box down below. I'm also going to have links to the Eclipse board, the Enclosure, the Amazon links to where I got all of my little adapters and extra probes that aren't on Digilent's website. That's a wrap for 2023. So thanks for this little project and review with me. And thank you, Digilent, for sending me all the cool stuff and sponsoring this video. And I will catch you guys in 2024. Bye. Is that good? Okay, bye!